In November of 1519, a column of Spanish soldiers crossed the pass between two volcanoes, Popocatépetl and Iztaccíhuatl, and looked down into the Valley of Mexico. What they saw stopped them. A lake stretched across the valley floor, and in the center of that lake sat a city. Causeways radiated from it like the spokes of a wheel. Temples rose above a precise urban grid. Smoke curled from thousands of hearths. Canoes, hundreds of them, moved through a network of canals so orderly they resembled streets. Bernal Díaz del Castillo, a soldier in that column, would later write that some of his companions asked whether they were dreaming. He noted that the men reached for the only comparison they had, the enchanted cities from Amadís de Gaula, a popular romance novel. Trained soldiers who had already conquered Cuba looked at this city and reached for fantasy fiction, because reality had no frame for what they were seeing. That city was Tenochtitlan. Its population was around 200,000. Scholars debate the precise figure, with estimates ranging from 150,000 to 300,000 for the island city alone. But take the conservative middle, 200,000 people. London at that time held perhaps 60,000. Paris, the largest city in Western Europe, had maybe 200,000 on a good estimate. Tenochtitlan was not a backwater outpost of some marginal culture. It was one of the largest cities on Earth, and it sat on a lake. You have probably heard this comparison before, but what you may not have heard is how it actually worked. How the Mexica, the people we call the Aztecs, solved the specific engineering problems of building a metropolis on water in a saline lake basin with no iron tools, no draft animals larger than a dog, and no wheel. Because the solutions were not mystical. They were brilliant, practical, and in several cases, more advanced than anything contemporary Europe had managed. Start with the food. Tenochtitlan fed its population using chinampas, often mistranslated as floating gardens, though they did not float. They were stationary raised agricultural beds constructed in the shallow margins of the lake. Workers drove stakes into the lake bed, wove wattle fences between them, then layered lake mud, decaying vegetation, and soil until the beds rose just above the waterline. Ahuejote willows were planted along the edges, and their roots grew down through the beds and anchored them to the bottom. The result was a network of rectangular plots surrounded by canals. Rich, dark, perpetually irrigated earth that never needed to go fallow because the lake mud kept replenishing the nutrients. The productivity was staggering. Where European dryland farming yielded 1 or 2 harvests a year, chinampas could produce as many as 7. Maize, squash, amaranth, beans, chili peppers, flowers, growing simultaneously in different stages on adjacent plots, tended from canoes. The system was not an Aztec invention. Earlier, lakeside communities in the basin of Mexico had developed it over centuries. What the Mexica did was scale it, systematize it to feed 250,000 people in a city that had no farmland in the conventional sense. They did not farm beside the lake. They built the farm inside it. Now, consider the water. Lake Texcoco was saline. You cannot drink salt water, and you cannot irrigate with it. The Mexica solved this with 2 aqueducts. The primary one ran from the freshwater springs at Chapultepec, about 3 kilometers west of the city, along a causeway to the island. It was a double-barreled system, 2 parallel channels, so that one could continue supplying water, while the other was shut down for cleaning and maintenance. This is not a primitive workaround. This is redundant infrastructure engineering. Modern water utilities use the same principle. Cortés himself described it in his letters to Charles V, noting how fresh water was distributed to households and public fountains throughout the city. And then there is the detail that tends to silence a room. Tenochtitlan had organized waste collection. Human waste was gathered by canoe and transported out of the city for use as agricultural fertilizer on the Chinampas. Streets were swept daily by a workforce Cortés estimated at 1,000 people. Public latrines lined the causeways and major thoroughfares. This is documented not only by Cortés, but by the Florentine Codex, the encyclopedic record of Aztec life compiled by the Franciscan friar Bernardino de Sahagún, working with Nahua informants across decades in the mid-16th century. London, at that same moment in history, was dumping its sewage into the Thames, the same river from which it drew its drinking water. London would not build a sewage system until the 1860s, after the Great Stink of 1858 forced Parliament's hand. The Aztecs had solved that problem 3 centuries earlier, not because they were wiser in some abstract sense, but because their geography demanded it. Contaminate Lake Texcoco, and you destroy the Chinampas, poison the drinking water, and kill the city. Their sanitation system was an engineering response to an existential environmental pressure. It was also, by any honest measure, superior to what Europe managed for another 300 years. There is one more piece of Aztec engineering that most people have never heard of, and it may be the most impressive of all. Nezahualcóyotl, the philosopher king of Texcoco, the man whose Nahuatl poetry survives in written form, and whose intellectual reputation in 15th century Mesoamerica was roughly equivalent to a Renaissance polymath, directed the construction of a dike across Lake Texcoco, 16 kilometers long. It separated the brackish eastern waters from the fresher western waters near Tenochtitlan, essentially re-engineering the chemistry of the lake to create a controlled freshwater zone for the city. It also functioned as flood control, a 16-kilometer dam across a lake to separate salt from fresh. This is hydraulic engineering on a scale comparable to the Dutch polder systems, and it predated them by over a century. These were not people fumbling in the dark. These were people running institutions. The Mexica maintained mandatory schooling. The Florentine Codex describes 2 systems, the Calmecac for noble children, with a curriculum that included astronomy, law, rhetoric, history, and calendrics, and the Telpoccali for commoners, focused on warfare, trades, and civic duty. Girls received formal education as well, in separate institutions. Mandatory universal education in 15th century Mesoamerica, while Europe's universities served a vanishingly small fraction of the population. Now, let your eye move southeast about 1,000 kilometers to the lowland jungles and limestone highlands where Maya civilization had been flourishing for over 2,000 years before the Aztecs existed. The Maya achievement is different in character. Where the Aztecs built a spectacular city, the Maya built a spectacular way of knowing time. They did not use one calendar. They operated at least 3 interlocking cycles simultaneously. The Tzolk'in, a 260-day ritual cycle. The Hab, a 365-day solar cycle made of 18 months of 20 days, plus a 5-day period called the Wayab. These 2 cycles meshed to create the calendar round, which repeated every 52 solar years. And for longer spans, they developed the long count, a vigesimal system, base 20, counting days from a mythological creation date that corresponds to August 11th, 3114 BCE in our calendar. The long count allowed the Maya to place any event on an absolute timeline, stretching thousands of years into the past and future. No contemporary European system could do this. You may have heard that the Maya calendar was more accurate than Europe's. This is true, but not in the way most people think. The Maya hub remained a flat 365 days, with no leap day correction. But Maya astronomers working over generations at sites like Copan and Palenque, calculated the true length of the solar year to approximately 365.2420 days. The Julian calendar, which Europe used from 46 BCE until the Gregorian reform of 1582, assumed 365.25 days, drifting by a full day every 128 years. Even the Gregorian correction of 365.2425 is slightly less precise than the Maya figure. The precision existed not in a reformed civic calendar, but in the astronomical tables and supplementary calculations the Maya maintained. Institutional knowledge passed down and refined across centuries. This was not stargazing. It was systematic empirical observation sustained across generations. The caracol at Chichen Itza has window alignments that correspond to the extreme positions of Venus on the horizon. The Dresden Codex, one of only 4 Maya books to survive the colonial destruction, contains Venus tables that track the planet's synodic period across 104 years, with an accumulated error of roughly 2 hours. 2 hours over a century, with no telescope, no lens, no metal instrument. Just the naked eye, crossed sticks for sighting, bark paper codices with dot and bar numerals, and the institutional patience to keep watching for longer than any single human life. And here is the detail that recalibrates everything. The Maya independently invented the concept of zero, represented by a shell glyph functioning as a true positional placeholder in their base 20 number system. By at least the 4th century CE. This is one of only 3 or 4 independent inventions of zero in all of human history. Europe did not widely adopt zero until the 12th or 13th century through Arabic transmission of Indian mathematics. For 800 years, the Maya had a mathematical tool that Europe lacked. If you have ever heard someone imply these civilizations were primitive because they lacked European technology, hold that thought against the zero. Hold it against the Venus tables. Then let it go, because it was never a serious position. It was a colonial-era justification dressed up as common sense. The Maya calendar, incidentally, did not predict the end of the world in 2012. No classic Maya text describes that date as apocalyptic. The long count cycle ending on December 21, 2012, was analogous to an odometer rolling over, the completion of one great cycle and the beginning of another. The 2012 phenomenon was a modern invention grafted onto Maya chronology by people who understood neither. Now, move south, far south, into the Andes. Imagine you are standing on a road. It is paved with stone, roughly 4 meters wide, cut directly into a cliff face 3,000 meters above sea level. On one side, a retaining wall holds back the mountain. On the other, a drop you do not want to think about. Mist moves through the valley below. The road does not end. It curves around the mountain, and when it reaches a gorge, a suspension bridge of braided ichu grass carries it across. The bridge sags in the middle. That is not a flaw. That is how suspension engineering works. You can hear the river far below. This road is part of the Capacñan, the Inca road system. Approximately 40,000 kilometers of paved and maintained highway stretching from modern Colombia to central Chile, the full length of the Andes, the longest mountain chain on Earth. The Roman road system at its peak covered roughly 80,000 kilometers. The Inca built half of Rome's total in about a century, at altitudes that would leave a Roman legionary gasping, without the wheel, without iron tools, and without pack animals stronger than a llama, which can carry about 30 kilograms and will sit down and refuse to move if you overload it. The Inca did not use the wheel for transport. This was not ignorance. Wheeled toys have been found in Mesoamerican archaeological contexts. The rotational principle was known. The Inca chose not to adopt it because it was useless in their landscape. The Andes are steep. The roads include stairways carved into rock at high-altitude passes. Switchbacks climb thousands of meters in elevation. A wheeled cart on an Inca road would be a liability, not an asset. The decision was intelligent environmental adaptation, not technological failure. Along those roads, the Inca stationed relay runners called chasquis at tambos, way stations spaced roughly every 6 to 9 kilometers. A chasqui would sprint his segment, pass the message or package to the next runner, and the relay would continue. Colonial-era Spanish sources claim the system could move information at roughly 240 kilometers per day. Whether that specific figure is exact or Inca imperial propaganda filtered through Spanish chroniclers, the system functioned. Pedro Cieza de León, a Spanish soldier who traveled the Inca realm in the 1540s, described the road with genuine admiration. The storehouses at regular intervals stocked with provisions, weapons, and clothing. He compared it favorably to the Roman road system. He had no reason to flatter a conquered enemy. He was simply describing what he saw. And here is where the Inca story becomes genuinely strange. Strange in the way that forces you to rethink assumptions you did not know you held. The Inca administered an empire of roughly 12 million people across the most difficult terrain on Earth. They managed census data, tax records, military logistics, agricultural inventories, and, possibly, historical narratives. They did all of this without alphabetic writing, without hieroglyphs, without any visible system of marks on a flat surface. They used quipus, knotted strings, a primary cord from which dozens or hundreds of pendant strings hung in organized clusters. The strings were made of cotton or camelid fiber, dyed in multiple colors: browns, reds, whites, yellows, using cochineal for red, natural plant dyes for the rest. Knots were tied at specific positions along the strings, and the type of knot, its position, and the color and twist direction of the string all carried meaning. The numerical encoding was decoded decades ago. Knot types and positions represent units, tens, hundreds, and thousands in a base 10 system. That part is settled. What remains unsettled, and what makes this one of the most exciting frontiers in the study of human communication, is whether some quipus encode language. In 2017, the scholar Sabine Hyland, working with the community of San Juan de Colata in Peru, identified a quipu system that appears to encode phonetic syllables using combinations of fiber type and color. If this interpretation holds, it would mean the Inca developed a form of writing so radically different from anything in the Old World that we did not even recognize it as writing for 500 years. We cracked the math decades ago. The question now is whether these knotted strings also contain words. The answer is getting closer to yes. Felipe Guaman Poma de Ayala, an indigenous Andean writer who composed a 1,200-page illustrated chronicle addressed to the King of Spain around 1615, drew the Quipu Kamayuks, the record keepers, at their work. His illustrations, now preserved in the Royal Library of Denmark, are the only contemporary visual record of quipu use in an administrative context. The keeper's fingers move along the cords, reading. Reading what exactly remains the question. The Inca also solved a problem that would challenge any agrarian empire in mountain terrain: how to farm slopes too steep for conventional agriculture, and how to preserve food at altitudes where nothing stays fresh. Their answer to the first was the anden, the agricultural terrace, cut into mountainsides, supported by stone retaining walls, filled with transported soil, and irrigated by channels that captured glacial meltwater. The terraces at Moray are concentric circles descending into the earth, creating temperature differences of up to 15 degrees Celsius between the top and bottom. A feature some scholars interpret as an agricultural research station, a place to test crops at simulated altitudes. The interpretation is debated. The microclimates are documented. Their answer to the second problem was chuño, freeze-dried potatoes, spread on the ground at night above 4,000 meters, where temperatures drop below zero. During the day, workers tread them barefoot to squeeze out the moisture. Repeat for several days. The result is a lightweight, shelf-stable food that can be stored for years. Field rations for armies, emergency provisions for drought. They invented freeze-drying, not as a concept, as a scalable technology using nothing but altitude and bare feet. There is a bridge in Peru called Queshuachaca. It spans the Apurimac River Gorge. It is a suspension bridge made of braided ichu grass, built using techniques that date to the Inca period. Every year, the local community gathers and rebuilds it. They dismantle the old bridge and construct a new one from hand-braided cables, following methods passed down through generations. The bridge was inscribed as a UNESCO World Heritage practice. It sags in the middle, as it should. It has been rebuilt year after year for 5 centuries. If you ate corn today, or tomatoes, or potatoes, or chocolate, or chili peppers, or vanilla, or avocado, or squash, or beans, you ate something first domesticated by the peoples of Mesoamerica and the Andes. These crops now feed a substantial fraction of the human species. The agricultural knowledge that produced them was not incidental. It was the foundation for everything else: the cities, the calendars, the roads, the record-keeping, the empires. 7 million Maya live today across southern Mexico, Guatemala, Belize, and Honduras, speaking more than 30 related languages. 1.5 million people in Mexico speak Nahuatl. 8 to 10 million people across Peru, Bolivia, Ecuador, and beyond speak Quechua and Aymara. These civilizations are not lost. They were never lost. The conquest disrupted them, devastated them. Smallpox alone killed an estimated 40 to 90% of the indigenous population in the century after contact. But it did not end them. The next time you cross a bridge, consider that someone braided the first one from grass across a gorge in the Andes and trusted it to hold. The next time you check a calendar, consider that someone tracked Venus for a century with nothing but their eyes and got it right to within 2 hours. The next time you turn on a faucet, consider that someone built a double-pipe aqueduct across a causeway on a lake 500 years ago, with the same redundancy logic your city's water department uses now. They solved these problems. The evidence is in the stone, in the strings, in the codices that survived the burnings, in the languages still spoken, in the crops still growing, and in the bridge still rebuilt every year by hand over a river that has not stopped running.